For this particular set of slides, our focus, our objective, our main objective is we will get to know the performance equations for the 3 ideal reactors that we will be covering, and then apply these performance equations in the design of these reactors. So when we design a reactor, we base it on the ideal the ideal reactor, and how it's going to perform, on what is the corresponding volume, what would be the corresponding mode of operation if the said reactor is to behave ideally. Of course, in the real setting, there will be lots of adjustments, but our design would still be based on the ideal reactors, in which later on we will derive the different performance equations. So when we speak of the rate equation, which will be appearing in the performance equation for the 3 ideal reactors that we're going to talk about, it's actually an intensive measure. So the rate equation is not dependent on the volume or in the amount of the reacting mixture that we are to analyze, and then use the corresponding interpreted data from the experiment in the design of the said reactor. So it's an intensive measure. Now it tells us how rapidly a particular component disappears or forms. So if it's a reactant, of course, it's expected to disappear. If it's a product, it's expected to be formed over a period of time. Now, in a given environment, that's a function of the conditions in that particular environment. So how a species is being consumed, how it is being produced, given the condition or given the environment in which that particular species is to react on. Now, when you speak of the rate equation, somebody also asked me this: how do you differentiate a rate equation from a rate law? So when we speak of a rate equation, it's a differential equation. Whereas when we speak of the rate law, you have an equation still, but it does not have the appearance of the derivative. Now, what is it that you need to know in reactor design, or what to know in reactor design? Actually, I've given this to you at the start in the orientation at the start of the class. So in here, we are to determine the size and the type of reactor that will facilitate a particular reaction, and what should be the corresponding method of operation or mode of operation. So when we speak of mode, would it be steady state? Would it be batch? Would it be semi-batch? So it depends on the design. Now, what are the factors to consider in predicting reactor performance? So what are the variables that appear specifically in the performance equation? They may not be explicitly written in the performance equation, but the variables that appear in your performance equation are actually dependent on these two. So these two factors are temperature and pressure. They are the primary factors, although we need also to look into the endothermic or the exothermic nature of the reaction. Would it be liberating heat? Will it be needing heat? So that's also needed in reactor design. And we also need to, of course, in relation to the endothermic and the exothermic nature of the reaction, we also need to know the rate of heat addition or removal to or from the system. So what's the rate in which this heat is being removed or added to our system? Now, we need also to look into or consider the flow pattern of the fluid in the vessel. But the two main factors are these two, the temperature and composition. But these three are also things to look into when we design the reactor. Now, in terms of types of reactors, so we classify them either as batch, continuous, or industrial reactors. Actually, your continuous reactors here are also in the industrial reactors because they are commonly used in the industry. So when you speak of the continuous reactors, so they are operated continuously. So we have the CSTR, or the constantly steered tank reactor, otherwise known also as a mixed flow reactor or another name is back mix reactor. So all referring to the same thing. Now we also have what we call the tubular reactor, commonly known as the plug flow reactor. So tubular meaning in this case, our reactor resembles that of a cylinder or a tube. Now, these two are also found in here. So you could see that you have the CSTR here and the tubular reactor, and you have the simple batch reactor also that is being used in the industry. Later on, you will know what's the difference in terms of use or application of these three industrial reactors. Now, when you speak of tubular reactors, so they can be classified as also packed or fixed bed reactors or fluidized bed reactors. So our fluidized bed reactors are oftenly operated based on the plug flow operation, okay, or how the fluid inside the reactor contact each other and produce the product is that of a, or compared to that of the plug flow or tubular reactor. So these are the types of reactors. What we're going to study would be the CSTR and the tubular reactor. In the entire midterm, we have discussed already the batch reactor. Okay, so now our focus will be on the CSTR and the tubular reactors. From time to time, we may compare the performance of these two with the simple batch reactor. So there are problems actually that will ask you to compare how will the conversion be, or what size of the reactor would be if it's facilitated in a batch reactor, or compared to a plug flow reactor, what would be the size, or something like that. So we will not totally forget that everything that we have learned in midterm regarding batch reactor will still be used. I say like 95% of you have learned in midterm will still be used in the design of the ideal reactors, because our rate law is actually based on the interpretation of the experimental data that we have gathered when we experimented using a batch reactor. That particular rate law will be applicable to the same kind of reaction even if it's facilitated in a different environment. What do I mean by that? Even if you're going to perform that particular reaction in a tubular reactor or in a CSTR, its rate law is its rate law, even if that was derived using a batch reactor. So that is why I'm saying that what you have learned in midterm would still be your basis, will still be a big factor in here in end term, because you cannot design without the rate law. Now, when we speak of reactors where homogeneous reactions are facilitated or effected, then we can have all these three reactors. We have the batch, we have the steady state. The steady state, you will know in a while, will be the group in wherein your CSTR and your plug flow reactor will belong. And then we also have the unsteady state or the semi-batch reactor. But here in kinetics, we will not dwell so much on the semi-batch process. Our main focus is on the three ideal reactors, which is the batch, and the other two, which is under steady state flow, which is your CSTR and your plug flow reactor, all of which can handle homogeneous systems, systems in which you only have a single phase all throughout the reaction. Now, this is actually snipped through from what you have in Levenspiel, from our reference book Levenspiel. So in here, in letter A, that's how he represented the batch reactor. And letter B, that's your tubular reactor. But this B, this C, and this D are all steady state flow reactors. Okay, plug flow and CSTR. Now for letter E, you have here letter E, this one, it's semi-batch already. Now it would be easy to understand the difference between the steady state and the unsteady state operation later on when you see the animation on how mixtures are reacted inside the steady state reactors, and what's the difference with that of the unsteady state reactor, in which your semi-batch reactor is under the group of. Okay, so but then again, I will emphasize that our main agenda in this set of slides is to know how to design the batch, the constantly stirred tank, and the plug flow reactors. Now, again, this is another set of illustration taken from Levin's field. So these are the three ideal reactors, and this is our main focus. The batch, the plug flow or the tubular flow, and you have the CSTR or the MFR. Now, let's go to each one and what's expected in terms of their differences, what makes one unique compared to the other. So we first discuss the one that we have finished in midterm, and that's the batch reactor. And this is a simple animation of what's happening inside your batch reactor. Last part mentioned about some are operated at constant pressure. And how could that be? By varying the volume of the system inside your reactor. So that's for the batch reactors. And these are the things that you need to take note of regarding it. So it's an steady state operation, just like the semi-batch, or this one is just the batch reactor. So it's in steady state because there is a change in the composition at any time inside your reactor. It's also unsteady state because anytime we can change the mode of adding the reactants or the reactants inside the reactor, the same thing with the removal. So it's unsteady state. Okay, that's the same thing with semi-batch. Now, though at any particular time, the composition in the reactor is going to change because of course of the reaction, there is no spatial variation of concentration or temperature, meaning at any point inside the reactor, there is this uniformity in concentration, although over time the concentration changes. It's because the mixture inside the reactor is well mixed, so it's uniform. Now, however, the main drawback of using the batch reactor is it's mainly used only for small scale operation and is only suitable for slow reactions. So if your reaction is very fast, this reactor is not really suggested. Okay. Now, mainly, though not exclusively used for liquid phase reaction. So if you were listening to the video, we know that gas phase reactions can also be facilitated inside the batch reactor. Now, that's a reaction which is constant pressure, and how that is assured is by varying the volume of the mixture inside your reactor. So although mainly we can say mainly it's used for liquid phase reaction, but it's not exclusive for a liquid phase reactions. It could also be used for gas phase reaction. The thing with batch is it's like you're cooking something, you put everything inside, you allow it to react based on the time that you want it to react, then you withdraw it. So the charging and the draw off time together with the cleanup time so that your particular reactor can facilitate a different type of reaction is a thing to be considered with batch reactor. So time for putting in the reacting species, time to withdraw the product, and time to clean it up for the next operation. That's a drawback also for your batch reactor. The thing with it is since it's for slow reactions, it's for small scale operation, it's simple and needs very little supporting equipment. Okay? Not like the other two, the steady state primarily because they may need supporting equipments, especially when we speak of reactions that needs to have the addition of heat or there is a removal of heat in the mixture in the course of the reaction. So that's for the batch reactor. Now, this is your batch reactor from Levenspiel. That's the way he represented it. So you have the pi O. You know pi O, that's the total pressure of your system. If you have a gaseous reaction, VO is your initial volume. NaO is your initial number of moles. PaO is the initial partial pressure of A. And CaO, is expected to be zero at time equal to zero at the start of the reaction because, of course, it's expected that nothing yet was converted. So your CaO is zero. After some time t, then we change all our representations here with the subscript O. Now we took away the O, meaning it's not anymore time zero. It's not the original or the initial time. So we have everything here. That's for the representation that you have in our general reference book. Now we go to the steady state flow reactors. Actually, there's two of them. So the CSTR and the plug flow reactors are steady state flow reactors. So they are mainly used for industrial processes with large quantities. And when there is this fairly high or extremely high rate of reaction, these particular reactors are suggested. So when rate of reaction is fairly high to extremely high. Now, of course, supporting equipment is opposite with that of the batch. So supporting equipment needs here is great, but though we have this two downside with it, it has extremely good product quality control. So you can control the purity of the product, or shall I say, it's expected that the purity of the product that you are getting from this steady state flow reactors is much higher compared to that of the batch reactor. Now, it's widely used in the oil industry as suggested by Levenspiel. Now, of the two, so I have mentioned we have the plug flow and the CSTR. We're going to look into first the tubular reactor or the plug flow reactor. So the operation here is steady state. Spatial variation is in the axial direction but not in radial direction. Axial meaning the axis or the direction of flow of your reacting mixture inside your reactor is also your axis, or yes, is also your axis, and it is expected that there is spatial variation in concentration, specifically in the axial direction. But from the center of the axis outwards, that's referring to radial direction, the composition is not varying. So center of the axis outwards, from the center of your tube or your plug flow reactor, there is no change in concentration. That's radial direction. But along the axis, there is. Now, temperature control in this particular type of reactor is, however, difficult. And what is likable compared to the other two about this reactor is that it has no moving parts because you simply have a tube in this case. Okay, so let's look into how a particular tubular reactor operates. There's no voiceover in here, so I will discuss it as the video proceeds. So this is your tubular reactor here. As you could see, as the reacting mixture travels from this point here down, in terms of concentration, if you're going to look at the concentration, the reactant concentration decreases along the distance in which your particular reacting mixture traversed. Let me go back to that. And the product, on the other hand, the products or the product increases in concentration. So as the reacting mixture traverses this distance along your plug flow reactor, there is a decrease in the reactant concentration and of course an increase in the product concentration. I think it's self-explanatory, primarily because as the reaction proceeds, we are producing the products from the reactants. So this is a very simple illustration of a plug flow or tubular reactor. This particular tubular or plug flow reactor can be as small as a capillary tube. Now, the fluid in here flows through the reactor in an orderly manner without mixing or diffusion along the flow path. So it's as if, just like when we were in grade 1, we were asked by our teacher to fall in line and then put our hands in front of us. That way, nobody stays out of the line. No student overtakes another, or no student goes backward. So it's the same thing with the plug flow reactor. It's as if the fluid elements inside your tube or your plug flow reactor is moving in an orderly manner without mixing or diffusion along the flow path, which is along the axis also. However, we expect that as it moves along the axis or the flow path, the concentration changes. So axial changes in concentration, but not radial. Now, speaking of fluid elements, so if we cut a disc along your cylindrical plug flow reactor, if we cut a disc, it's comparable to a volume element. So these volume elements have the same residence time inside the plug flow reactor. So each elemental volume has the same amount of time that it has remained inside your reactor. Now, we have here the continuously steered tank reactor. So I think it's very self-explanatory. There's continuous steering inside the reactor. And it's also known as the back mix reactor. So steady state, just like the plug flow, the concentration at any point is uniform. So do not change with time. It can be used in series, but that's not yet covered in this particular set of slides. So we're going to handle cases in here. We're only talking about the single reactor, but your reactors later on the next set of slides can be arranged in series, in combination, or in same kind. So that is why it's placed in here. It can be used in series. Now, no spatial variation of concentration or temperature. So I have mentioned that already. Mainly used for liquid phase reactions. So mainly used for liquid phase reactions, so meaning like 98 to 99% of operation is the constantly steered tank reactor that is being used. Now, one thing that is notable about this reactor is it's used for viscous liquids. Okay, primarily because of the steerer. So any changes in concentration over time, especially for reactions that tend to go viscous over time, that is addressed in part, but not fully, by the presence of the steerer inside your reactor. So that's our steered tank or constantly steered tank reactor. Now let's look into how this particular reactor or how the fluid inside the particular reactor is reacting or mixed, or what's the contacting pattern of the fluids inside your CSTR.
Continuous stir tank reactors are open systems that operate on a steady state basis. Reactants are continuously introduced into the reactor, while products are continuously removed. CSTR are very well mixed, so the contents have relatively uniform properties like temperature, density, etc. throughout. Also, conditions in the reactor's exit stream are the same as those inside the tank.
Okay, if you have noticed in the video, the difference with the batch is as the reacting species is introduced inside the reactor, the product that is withdrawn is also continuously removed. Unlike the batch that you place everything inside, allow it to react, then after reaction time, the entire thing, the reactants and the unreacted reactants together with the products are all withdrawn together. So that's the batch. But in the case of the CSTR, it's different. Okay, so continuous addition, let's look at it again.
Tank reactors are open systems that operate on a steady state basis. Reactants are continuously introduced into the reactor, while products are continuously removed. CSTR are very well mixed, so the contents have relatively uniform properties like temperature, density, etc. throughout. Also, conditions in the reactor's exit stream are the same as those inside the tank.
Okay, that's it. Okay, that's the difference. Now you are able to compare the batch with the CSTR. There's no point in comparing the tubular with the CSTR because in terms of the equipment itself, they're really very different already. Okay, now as for the semi-batch, look at the semi-batch. That way you can compare the three, the batch, the CSTR, and the semi-batch. So what you have seen in the video actually is that there is control in the amount of reacting streams. So it could be that the first stream enters the tank first and the second stream enters next. Then they are mixed, allowed to react. Then that's the time that when a certain part already has reacted, that's the time that the withdrawal of the reacted and unreacted substances are being done. That's semi-batch. Want you to look closely again. So it could be that we'll have this, the first reactant here introduced followed by this, but they are allowed to react first here. Then that's the time that they are withdrawn. Okay. Unlike that of the CSTR wherein you have continuous addition of reacting species and continuous removal of the product. In the case of the batch altogether, it doesn't, it is not like you you put first the first reactant in the tank, then the second reactant in the tank, then allow them to react. No, they are put into your reactor together. That's batch. In the semi-batch, you can alter the mode of addition of a particular reacting stream. The same thing with, you can alter even the time in which you're going to withdraw the product. So it could be that you will allow it to react for an hour, then your next withdrawal will be for 30 minutes and the next would be 20 minutes. That is why it's called semi-batch. Not that it's something uniform in terms of withdrawal of products or addition of the reacting species inside the reactor. What is good about the semi-batch reactor is it offers good control of reaction speed. You have control of the reaction speed because you can control the time and the duration in which your reacting stream stays inside your reaction vessel. You can even control the time of withdrawing the product. Now, most often time it's used in colorimetric titration in the laboratory or semi-batch reactor, but the steel industry is using most of this type of reactors operated in semi-batch fashion. Now, we're done with the introduction and the three ideal reactors, how they behave, what's the difference in terms of how the reacting species are contacted and how the products are withdrawn. Now we're ready to learn the general mass balance equation, and if there's a need, the energy balance equation, so that we may be able to design properly our reactor. So when we speak of the general mass balance equation, it's the same kind of material balance that we're talking about in other subjects, in the other subjects that you have already encountered. So the rate of accumulation is placed in here on the last right side part of the equation. The rate of accumulation is added to the rate of reactant loss due to chemical reaction and the rate of reactant flow out of the element volume. Now, when we do material balance in the reactor, we consider an elemental volume. It could be in the form of a cylinder or a box, that elemental volume, but most of the time it's in the form of a cylinder because our reactors are in the form of tanks or cylinders. So that elemental volume we use to perform the material balance or the mass balance. So going back to what I have read a while ago, these three, the rate of reactant flow out of the element volume, the rate of reactant loss due to chemical reaction within. So this is out of the element volume, within the element volume, and the rate of accumulation of reactant in the element volume should be all equal. The sum should be all equal to the amount of reactant that entered that particular element of volume. So rate of reactant flow into element of volume. This is the same mass balance that you will see from Levenspiel. And this is our guide in getting the performance equations for our three ideal reactors. Our energy balance or our heat balance is patterned after the material balance. So the rate of heat flow into the element volume, or the rate in which energy is being introduced into the element volume, should be equal to these three as well, the sum of these three. The rate of heat flow out of the element volume, the rate of disappearance of heat by reaction within the element of volume. If your reaction is liberating heat, then that would be rate of disappearance of heat. Then we also have rate of heat accumulation within the element of volume. So the same, only that we change mass to heat in this particular second equation. Our primary goal, however, when we derive the performance equation, is use the first one, the general mass balance equation, because our performance equation is based on the general mass balance equation. Now let's go into each of our reactors and look into the different terms that are present in our material balance equation. So for a batch system, so you have this particular reactor representing a batch reactor. So we still have input equal to output plus the accumulation plus the rate of disappearance. The rate of disappearance is now accounting for the rate of reaction. It's the only term in here that has the appearance of the rate law, the rate of disappearance. The accumulation, if there is accumulated amount of species A that remains in your element volume, and then we account for that as well. Then we add that to the rate in which that particular species is withdrawn from the element volume. The sum of these three equated to the rate in which species A is introduced into our elemental volume. Okay, for the batch reactor, so that's for the batch system, the remaining part of the equation, there are four terms. There are four terms here. So the remaining terms would be the rate of reaction and the accumulation, the accumulated part. So there is no input and output. Okay, I think that's very self-explanatory. We don't have continuous addition of the reacting species here. We don't have continuous removal of the remaining unreacted A and the products in here. So this input and this output here are now zero. They are both zero. We don't have rate in and rate out. We only have this and this. So accumulation in this case is equated to rate of reaction. Now the rate of reaction is this. This one is your rate of reaction. Okay. Now, and this is your, if you were wondering why, where is this coming from? Why do we have to start with this? Actually, as written by Levenspiel, negative RAV is actually the rate in which most of A is changing over time. If you would transfer the volume in the right side here, by dividing the entire equation by V, this dNA over V will be your dCA dt. So that is why you have here concentration, the rate of change of the concentration with respect to time. Now, you know already how to deal with this. So you can have this one or this one. That is why I have placed two columns here for the batch, depending on what is provided in the problem. Let's say, for example, you have this. Now, the remaining number of moles of A unreacted after some time would be represented by Na. That's the remaining number of moles of A unreacted. And if you're going to write this in terms of the equivalent formula CA is equal to CAO times the quantity 1 minus XA, you will arrive at this particular equation. The V was transferred here, so there was division by V, so this is the V already. This particular NaO dXA is actually your DNaO times the quantity 1 minus XA. I leave that to you as an exercise because it's the same thing as if you change the CA here to Na, and this will be the resulting shall I say, set of terms on the right side of your equation. Now, if you will place the dt here, let me annotate so it would be clearer. This dt you can transfer here, and this Ra is placed here. So you have now dt, which is integrated from 0 to t, will be equated to NaO is a constant. So you see that NaO here. Then you have the integral from 0 to XA, 0 conversion to XA conversion at time t, all over 1 over negative RAV dXA. So the RA that you have here was transferred here already, together with the V that you have here, and then the XA. I'd like to ask a question. Why do you think was this DE, the DE which has the unknown function XA and time, processed in this manner? The time was isolated in the left side, and now the rate was placed in here. What do you think is the reason behind why we transfer the rate law on the other side, on the right side, with or together with the DXA? Why transfer RA here? Why not keep RA there and then DT is transferred there anyhow? Then you could still separate variables. DT can be integrated standalone and you keep RA there. Why is RA transferred on the right side? Anybody? Am I alone? Yes, let me see. Why do you think it was RA transferred here? Anyway, this is separation of variables. If you're going to look at the technique of differentiation of differential equation, why RA was transferred here? If I may ask, why not keep it on the left side, then just transfer dt there, and then the two will be together, then just integrate dt from 0 to t, leaving you with an NaO integral from 0 to XA of dXA over V on the right side. Why transfer RA here? Antoinette, why do we need to transfer RA on the right side? Why not keep it there on the left side? Why not?
Afternoon, Miss.
Afternoon.
Ng ano,
What do
para
you
gulo
think?
kay sa akon, Miss. Mas related, Miss, ang negative RA, Miss, kag ang XA, Miss.
Ka-related si RA kag si DXA. Is that what you mean?
Oh, yes, Miss.
Okay, so your guess is correct. The reason why, then that's just how it should be. It's a no-no to keep RA on the left side. RA should be transferred on the right side because this rate is in the form of rate law. For example, I write here KCA. This CA is dependent on XA. So you can write KCAO 1 minus XA. Okay? So Antoinette is very correct when she said it's because base means dependent si rate sa kay DXA. Hindi base dependent gid si rate kay conversion. So this RA changes depending on the rate law that will represent your particular reaction. So if it's second order, for example, this is second order. So we will place here 2 and you will place here 2. So your integral on the, in this side, your integral on the right side would be dxa divided by the quantity 1 minus xa squared. The rest are constants like this one, the k, the cao squared together with the nao. They are all constants. You can place them before the integral. Okay, thank you for that, Antoinette. Now my next question would be this. Why, let me change the color so there would be, why do you think this v has to be written after the integral sign, not before? Why write the v after the integral sign? Could it be not that we write it like this? Then I'll write the integral like that. What's the reason behind the v is written after the integral sign? Anyone? Why do you think we write the v after the integral sign, not before? Any volunteer? Okay. What about Jean, Arnica? What do you think is the reason why v has to be written after the integral sign, not before the integral sign?
Same man mi sa rate equation, naga-base man siya mi sa dxa.
The same sa rate equation nga naga-base. What do you mean base?
Ga-depend man sa mi sa dxa, ang volume.
Ang volume. Can you tell me why it depends on the XA, the volume?
Okay, if ang rate, di ba miss ang xa is ang ga-react.
Ang converted, ang na-convert.
Ang converted miss. So if ma-change ma miss ang na-convert, ma-change ma miss ang volume sa reactor.
Is that like 100% of the time? That if we have, that if a certain amount have been converted, the volume changes?
Not sure, miss.
Not sure. Okay. Sabi. Thank you. Thank you, Anika. So let's call on another one. Earl? Earl John?
Miss mi nga po, miss.
Yes.
Wala idea, miss.
Wala gid idea si Earl. Sige, bemamangkot to sa may idea. Si Jess, the Asis. Jess?
Hello, miss. Good afternoon.
Good afternoon, Jess.
Kasi, miss, para ma-cancel out, miss, ang unit, miss, na volume, miss, sa ano, ma-cancel out lang ang volume, bala, miss, na unit.
Di kung ipagwa to siya ihor before the integral sign, na-cancel out ang unit, hindi.
Ma-cancel out ng dura, miss.
So, meaning, in terms of the reasoning nga, kay para, miss kung mag-dimensional analysis, mag-uniform ang units ang left side kag right side, pwede man gyapon siya mag-cancel, miss kay ibutang mo siya before sa integral sign. So, ang question nga, after siya sa integral sign. So actually, Arnica has already an idea, but she was not able to follow it to the end in terms of the reason behind why V has to be written after the integral sign. Let me see if base matapos ni, let me see, kinang mga katawan niya, dutay na lang. Si Jules Santiago. Jules? Yes. Do you have any idea why V has to be really written on right after the integral sign?
Wala, miss.
Wala idea si Jules. Sige. Si Katrina. Katrina.
Hi, miss. Good afternoon. For me, miss, kay ang volume is proportionate sa conversion, miss.
like this. That's only B. Is this what you mean?
Maybe, miss.
Amo na sa?
If kay for me, miss, hindi constant pero volume, if ma-change sa with conversion, amo nang after siya, isang integral sign.
Okay, again, it was not able to get it. Kay?
Amo naguro, miss, nga ang V is after sa sang integral sign because hindi constant and ang volume kag ga-depend sa on conversion.
Okay. So, is this ng variability in the volume all the time? Is this all the time, Katrina? Like the linear variability of your volume, is this all the time?
Hindi ko sure, miss, pero base, miss, if hindi constant ang volume.
Saan o hindi nga constant ang volume?
Wait, dayan kita.
Saan o siya hindi naga-constant ang volume? Like,
Kung liquid phase,
con?
hindi ka constant, miss?
Hindi siya ga-constant ang volume.
Kung gas phase, miss.
Very good. That's the thing that I was asking a while ago from Arnica. The reason why you have to write the volume, thank you for that, Katrina, after the integral sign, it's because in the case of gaseous reactions like 95 to 98% of the time, the volume is varying. That is why there is a need for you to write it right after the integral sign because the expression for the volume at any time is now dependent on conversion. So it has to be written here. If you have written it before the integral sign, actually you won't have a problem if your reaction is liquid phase. So that is why I asked Arnica a while ago, is it like all the time that the volume is changing? The answer is no. Because if your reaction is liquid phase inside the batch reactor class, there's no need for you to write it after the integral sign. It can be written before the integral sign because volume for liquid phase reaction is always constant. But in the case of gaseous reaction, it can be constant, but most of the time it's not constant. So for it to be safe, always write it after the integral sign. Anyhow, if you have realized that, oh, this one is liquid phase, I might as well transfer it before. Because it's a constant, you will see that it's a constant. So you can write it before. So now your equation, I will erase everything here. So that's the reason behind why this V, it's very important, this V and this RA has to be really written after the integral sign. Okay, this is your performance equation for a batch reactor. It allows you to solve for the time wherein a certain degree of conversion was already reached by your reacting mixture. Now, this is just one equation. It could also be in this form. So in this form, you can see, class, that you have a very simple dCA dt equivalent also to this one because these two are just equivalent of each other. Then you just change the Ca here to CaO times the quantity 1 minus XA. Then again, transfer the dt on the left side, just like what's done in here on the other set of formula, and the Ra in here. You have noticed that CaO was written before. You can see here it was written before because it's automatically assumed in this particular formula that you have a liquid phase reaction. So what I'm trying to say, to be safe, if you have a liquid phase reaction, have this particular performance equation memorized, or you don't need to memorize because if you know how to derive and write the expressions in here, there's no need for you to memorize. So this is your performance equation for a liquid phase reaction in your batch reactor. This one is your performance equation for a gaseous reaction in a batch reactor. So you have two sets of formulas to choose from depending on the system that you placed inside your batch reactor. Okay? Any questions so far for the performance equation of the batch reactor? Okay, there's none. So we will have a 3-minute break, or you can make it 5 minutes. Then we will transfer to the link that I provided for you for our dry lab schedule. Okay, so I will stop sharing for now. We will continue it on the period 1:30 to 2:30. Okay, see you in a while, class.